Today we have Dmitry Kogan from Stanford University to give this talk. Dmitry is a fifth year's PhD candidate at Stanford. His supervisor is Dan Bonnet. His research interests are in cryptography and computer security. Dmitry holds an MSc in computer science from the Weizmann Institute and a BSc in mathematics, physics, and computer science from the Hebrew University. He received the Best Young Researcher Paper Award at Eurocrypt 2018, TCC 2019, and Eurocrypt 2020. The talk today is about private blocklist lookups with checklists, which appeared in Usenix earlier this year. Now I pass the stage to Dmitry.
Thank you so much, Changyu. Thanks for inviting me, and thanks everybody for being here. Today I will be talking about private blocklist lookups with checklists, and this is joint work with my colleague Henry Corrigan-Gibbs. And during the talk, please feel free to ask questions. I'll be happy to take questions throughout the talk and at the end. So the problem that we're concerned with, blocklist lookups, the setting is that we have a server that holds some kind of block list of strings, and the client holds a string that it wants to check against the server side block list. And the key is that the client's string is private, and so the client doesn't want to reveal to the server which string it's checking. And this very general problem actually appears in multiple examples on the web. So for example, a browser might want to check whether a certificate presented to it by a web server appears in some server hosted list of revoked certificates. And the browser might not want to reveal to that service provider of the certificate revocation list which websites that the user is visiting. Another example is that, again, the browser might want to check whether a password that the user chooses appears in a list of compromised passwords on some service provider that hosts such kind of password dumps. And finally, the application that we'll actually focus in a bit more detail today is safe browsing. So in safe browsing, Google, the service provider, crawls the web and compiles a list of dangerous URLs. These are URLs of websites that are used for phishing or for hosting malware. And for each such dangerous URL, the server stores a SHA-256 hash of some canonicalized version of that URL. And then participating browsers can protect the user from visiting those dangerous URLs. The way they do it is that whenever the user types in some URL, or even for any resource that the browser is about to fetch, the browser wants to check whether this URL appears on this server-held block list of dangerous URLs. And so kind of schematically, what happens is that the browser can query the service provider, and if the URL that the user is about to visit is on this block list, then the browser kind of warns the user and prevents them from visiting this website. And this is a little bit in some, what I said now is a little bit of a simplified version. In practice, there's a few more details. So for example, the browser doesn't just send the URL in the clear to the server, it actually sends a shortened 32-bit hash to the server and then gets back the full hash. Then it can then check against the actual full hash of the URL. And also to reduce the load on the server and to reduce the latency for the client, the browser actually downloads a kind of a compressed list of this database of dangerous URLs. And in this compressed list, every dangerous URL is represented by a shorter hash. And so basically, the browser can kind of easily rule out most of the URLs just by seeing that they are not on this shorter list. Whereas if the URL is on this shorter list, then the browser actually needs to go to the server and check that this is whether it's a true positive or a false positive. But kind of regardless of the details, the key thing is that still during the normal browsing, the browser sends some partial information about the URL that the user is visiting to the service provider, and this kind of presents some sort of leakage about the user's browsing history and compromises partially the user's privacy. And this is the specific example that we actually target in the implementation of our system. So let me just be a little bit more formal about what are the requirements of this private blocklist lookup problem. So the first requirement is correctness, meaning that an honest client interacting with an honest service provider should correctly learn whether the client's query appears on the block list. And this should happen either always or, let's say, with some overwhelmingly high probability, which is close to 1. The second requirement is privacy for the client, meaning that even if the server is malicious, the server should learn nothing about which string the client is querying. And we can model this a bit more formally, like we do in cryptography, just saying that for any block list and any pair of query strings S and T, the view of the server when the client is checking string S should be computationally indistinguishable from the view of the server when the client is checking string T. And finally, we want our system to be efficient. Namely, we want to minimize parameters such as the latency, the communication, the computation for both the client and the server, and the storage for both the client and the server. And in particular, one thing that is not a requirement, at least not initially, is privacy for the server. The reason is that we can treat the list of this block list that the server hosts as containing some public information. And in some cases, you might want to additionally provide some sort of privacy for the server, but this actually turns out to be not that difficult if you can construct a system or a protocol that meets all the 3 requirements that I listed. And in the paper, we discuss how this extension works. And so in this work, we present a system for private blocklist lookups that satisfies those requirements. Namely, our system builds on a new type of private information retrieval scheme in which the client leaks no information about its query to the blocklist server. And in particular, we also improve the efficiency of our system compared to what would have been possible with previous state-of-the-art PIR protocols using this new type of PIR scheme called offline-online PIR. I want to say that kind of one main, perhaps, assumption or caveat in our system is that it requires 2 non-colluding block list servers, where each server holds a replica of the same block list. And crucially, the security requires those 2 servers not to collude. In practice, this means that the entities operating the server should be, maybe commercially competing companies, maybe Google operating one, and then Cloudflare or some Let's Encrypt or some kind of organization operating the second server. And I'll also talk about basically our implementation of this blocklist lookup system within the context of safe browsing. So that's that's the plan for the talk. The first part, I will talk about offline-online private information retrieval, which is the main tool that we use in our work. We'll then talk how to turn this more theoretical type of protocol into a practical protocol and specifically handle dynamic databases that keep getting updates. And finally, I'll discuss the implementation and the evaluation. Are there maybe any questions about the problem setup and the plan for the remainder of the talk? Okay, so let's continue and let's talk about offline-online private information retrieval. So two-server private information retrieval is a cryptographic protocol introduced by Shor, Goldreich, Kushilevitz, and Sudani in 1995. In classic private information retrieval, 2 servers or more hold identical replicas of that same database. And for now, think about the database as just being an n-bit array, meaning every record in the database is just a single bit. But however, there's kind of standard extensions in which we can implement support to larger database records, or actually, instead of an interface of an array, we can also use PIR to provide an interface of kind of this dictionary lookups that we need to do, in particular for our block list applications. And this can be done using standard techniques from the literature, for instance, using hashing. But for the remainder of the talk, you can just think about PIR as this kind of array lookups by index. And if every record is just a bit. So the client basically gets the client's input is an index from 1 to n, and then the client talks to both of the servers, and then from the responses, it needs to be able to reconstruct the value of the database record x sub I. And as I mentioned before, in multi-server private information retrieval, security only holds if the servers non-collude, meaning the view of every server on its own should provide no extra information to that server about which index the client is reading. And ever since the introduction of PIR in the seminal work, there's been a long line of work improving the communication complexity of PIR. And today we have very efficient private information protocols in terms of their communication. In particular, you can get something like order log n of communication, where n is the size of the database. And the main tools these state-of-the-art PIR protocols use is distributed point functions. However, there's one caveat in standard PIR protocols, namely, in all those protocols that we've kind of developed over the years, the server computation is very large. In particular, in those protocols, the servers needs to scan the entire database to respond to each query by the client. And this is very inefficient because you can imagine it's like for every query you need to do work which is proportional to the size of the database. And to make things work, this is actually not just some kind of coincidence. There's actually a lower bound from a work by Beimel, Ishai, and Malkin that shows that the server must do omega of n work to respond to a user query. And the intuition behind this lower bound is basically if the server doesn't touch a particular bit in the database while responding to the query, then the server learns that the client cannot be reading this bit that the server isn't touching at this point, and so kind of doesn't even know whether its value is 0 or 1. And this is just this kind of a simplified version of this lower bound, but in fact, it's pretty strong. It holds even if you allow for many non-colluding servers, and even if you're willing to make cryptographic assumptions and settle on computational security and not just information theoretic security. So kind of one approach to mitigate the computational inefficiency of PIR is this new type of private information retrieval called offline-online private information retrieval, which we introduced in our previous work last year. And the basic idea of offline-online PIR is that the client and the servers first perform an expensive offline phase, but that offline phase only needs to happen once. And then after this offline phase, the client can subsequently query the database, where now each query is much cheaper in terms of the server-side work. So I now want to give a little bit more detail about how these offline-online PIR schemes work and what exactly is the model. So the first phase of the protocol is this offline phase that I mentioned. Here, the client talks to one of the servers, and the server provides it with some piece of information about the database, which we call a hint. And generating this hint still takes the server linear time. So we don't completely eliminate the linear work from the system. However, there's two key things. First, the server only needs to do this expensive phase once per each client in the system, and also it can do it basically out of band and then overnight, where compute is cheaper versus online when the client needs to get responses fast. And you can think about kind of the size of the amount of the communication and the size of the hint in our protocol as being roughly square root of n. So there's an additional multiplicative factor of the security parameter lambda. But you can think about it as basically some square root communication, square root of n, where n is the length of the database. So after this offline phase, the client downloads this hint and stores it. And then in the online phase, the client can now use this hint to actually do private queries to the database. So now the client gets its input index I, the index of the record it is interested in, and then it uses its locally stored hint to generate its queries to the two servers. And then from the responses from the two servers and the locally stored hint, the client can now recover the value of its bit of interest, of record of interest, x sub I. And crucially, now in the online phase, both the work of the servers and the communication are all sublinear in the database size. And as I mentioned, in our offline online protocols, the client can repeat this online phase multiple times without having to repeat the offline phase. And so even the expensive linear time work that the server did in the offline phase can be amortized over multiple queries. And I should just mention that we're not the first one to consider some sort of offline-online model to PIR. However, previous protocols either required additional storage on the server or still required linear time in the online phase. And here, one of the key properties of the protocol is that the servers still store the database in its original form. They don't need to store some extra information as a result of running this preprocessing. All this preprocessed information is in some kind of captured in this hint that the client stores locally. If there are any questions about the model, that please feel free to ask.
Yes, I have a question. So when you do this offline computation, is that interactive or not?
So you can imagine that the only thing that the client sends is kind of a random seed that does kind of to a pseudo-random generator that the server can then use. When I'll show the protocol. But in fact, you can have the servers, if you're comfortable with having the server generate the seed itself, then the server can prepare and run this thing out of band and then only send the hint to the client. So you can kind of do both. I mean, if you do it ahead of time, then the server needs to store those hints and before it sends them to the client. Whereas in our model, we just think about that the servers don't need any storage, so they just do it interactively with the client.
Okay, and another question is, what if the database changes?
Yeah, that's a great question. I'm actually going to talk about it in next part of the talk.
Okay.
In a little while. Yeah.
There is one question in the chat. It says, do the two servers need to store the same data? I guess that is yes. That is yes for that question. And the second question is, they cannot communicate with each other, right?
So yeah, that's a very good question. So you can think about this basically. The servers they can communicate they can communicate to do that, to let's say to process updates to the database and to coordinate on the database. What they mustn't do is they mustn't send they mustn't misbehave jointly. So for instance, the one server shouldn't send information about the client's query which is considered private to the client to the other server, but everything about the public database they can send messages. Maybe when there's an update, say let's now rolled our database to the next version, this kind of stuff, as long as they're not sending information about the client's private query.
Okay, and Sia, you want to ask a question?
Yes, thanks, Timo. So subsequent to that question, do the servers need to know which other server the client is communicating with?
No, you can imagine like maybe, in the simplest, I will talk about updates later on, but let's say in the static database case, you can think that the only thing that each server needs to know is what is the database and basically pre-agree on the protocol with the client. And then it could be, potentially different servers throughout different organizations, as long as they all follow the protocol and they agree on the same database. They don't need to know anything about other servers in the system. They don't need to communicate with other servers in the system. That's in the static database case. If you have updates, then you somehow need to agree on versioning the database, maybe that kind of stuff.
All right, thanks. Yeah, that makes it very strong for private browsing, because potentially you can have I don't know, hundreds of servers providing this service, and they don't even know who the second server is. All right.
Right. So
to collude with, you know what I mean.
Yeah. That's a good point. And yeah, in particular, like it's not like a multi-party computation protocol when everybody needs to be online and talk to each other and know who all the other participants are. That's
sure.
that's kind of the benefit here.
Thank you.
Okay, yeah, thank you so much for the questions. Yeah, it's great questions. So let's just see kind of the summary of the more qualitative parameters of our scheme. So which I'll present, I'll give the technical details of our scheme in a bit. So our scheme achieves square root n, I already mentioned square root n amortized time per query, square root n communication per query, and square root n storage, extra bits of storage on the client. And you can see here that the more basically the more concrete terms. But however, we actually have an extra improvement in our protocol in which we can reduce the online communication to be logarithmic in n instead of square root of n, again with this multiplicative factor of the security parameter. And here we basically use this new cryptographic primitive called puncturable sets that allows us to compress the communication even further. However, this comes with the downside that the storage and the client time increase to be larger than square root of n, to say something n to the 5/6. So you win on communication, you lose on client resources. And very recently, there's actually some new work by Shi et al. That show how to avoid this blow up and get the best of both worlds. So kind of logarithmic communication and low storage and low client time. The caveat is that their construction uses a bit heavier tools. So they use privately punctuable pseudorandom functions that you can construct from learning with errors. So it's a bit less, it's not quite yet practical, but asymptotically, it's a huge progress. And maybe, there's more progress on the way. So let me now kind of finally describe the details or the basic details of how the scheme works. So in the offline phase, the client begins by sampling m random subsets of the universe of indices from 1 to n, where each subset is of size square root of n. So you have m subsets. We'll set the parameter m later on. Each subset contains some square root n numbers from 1 to n. And then the client sends the description of those subsets to the first server, to the offline server. And the offline server computes the hint, which consists of m bits, 1 bit for each subset, where the jth hint bit is the parity of the database bits indexed by the set Sj. So you have 1 parity bit for each subset, and the server then sends those m parity bits back to the client, and the client stores as its hint there are kind of this collection of sets and the parity bits of the database that these sets point to. That's the offline phase. Then in the online phase, to read a particular record I from the database, the client first searches through its local collection of hints to find a set that contains index I. If none of the sets in the local connection contain I, then the client aborts, output fail, and we'll see how to account for these failures in a bit. Otherwise, it finds some set Sj that contains I, and as a strawman, first consider the case where the client basically removes index I from the set Sj and sends this set of size square root n minus 1, the set Sj with I removed, to the second server, to the right server. What the right server does, again, it computes the parity of the database bits indexed by the set S prime and sends back this answer A to the client. And now the client has at hand 2 bits. It has the parity bit Hj that is basically the sum of all the database records indexed by the set Sj. And it has the response from the server A, which is basically the parity of all those same bits, except record I, bit I, is missing. And so the sum of those two bits, mod 2, gives you exactly the value of the database bit x sub I. So the problem is with this strawman's approach is, even though it's correct, it's not quite secure. And the reason is that it's not quite secure is actually that the way that I described, that this set S prime that the right server will see will never contain the index of interest I of the client. And so basically this provides some partial leakage on I to the server that learns that index that the client is interested is not in the set S prime. So you get some partial information. And to remove this partial leakage, what we do is that with some small probability proportional to the set of to the size of the set S prime, we actually just send a set that contains index I. So with most cases, the scheme is going to behave as the strawman. So this I is going to be removed, but with some small probability, we'll keep I in the set, and the server will see will sometimes see I, and we'll see how this helps us in the security analysis. Any questions about kind of the mechanics of the scheme?
One question is why this is square root n, the size of this subset?
Great question. Yeah, we'll see. I'll do the efficiency analysis in a bit. Yeah, that's good. Yeah. Thanks for the question.
Thank you.
So let's first look at correctness. We actually saw that there are two failure events that we already mentioned. The first is if this collection of sets doesn't include I, the client abort, the scheme fails. But this, we can make this probability, we can drive it down to be negligible in the security parameter by choosing the number of sets to be something like lambda square root of n, and then using a standard balls into bins argument, you see that the probability that this collection of sets doesn't cover the entire universe from 1 to n is negligible. So that's fine. The second failure event is this basically this tweak that we introduced, with which this event in which we keep index I in the set. And now, when this happens, this correctness equation that we had on the previous slide no longer holds. And this is actually happens with probability of roughly 1 over square root of n, which is not negligible. And there are two ways to work around this failure event. The first one is to basically repeat the online phase in parallel lambda times, each time kind of tossing this coin at random, and notice that you only need one of the reads to succeed, because you know when you fail, you know when you succeed. If one of them succeeds, you just use the value that you learned from there. And this introduces another factor of lambda in the online phase, but drives down the failure probability to be negligible. In this kind of recent paper, we actually we have a way to avoid this lambda times blow up in the online phase, which in practice would be a slowdown of more than 100. And we have a more complicated, a slightly more complex scheme that avoids this this failure in the online phase. And if you're interested, please check out the paper. In terms of security, so the security against the first offline server is just immediate, because whatever the server sees is just a collection of random sets that doesn't have anything to do with the index I that the client is trying to hide. And then in the in the online phase, this is basically this tweaking comes into play, because let's look now at the set S prime that the server sees. The way that we construct this set basically makes this set look like a uniformly random set of size square root n minus 1. The reason it's of size square root n minus 1, because remember, we started with sets of square root of n, and then we always remove elements. And let's just look at the event of whether this index I is contained in the set S prime. So the way that we choose our probabilities is that I is only going to be contained in the set with the small probability of square root n minus 1 over n. And this is exactly how you would expect a random set to behave. So a random set of size square root n minus 1 contains any fixed element exactly with this probability, which already means that kind of the server cannot look on whether which elements are in the set to try and guess I. And you can make this argument a bit more formal and show that S prime is actually a uniformly random set. And then we go, we're just left to analyze efficiency, which is what Changyu actually asked about. So let's look what happens if the offline is here. We already set the number of sets to be lambda times square root of n. However, just sending the sets explicitly would be prohibitively expensive. This would be like more than n bits. However, these sets are basically random sets that the client just generates at random. And what the client can do, it can just send a random seed to the server, and the server will use a pseudorandom generator to expand the seed and sample those random sets. And this will shrink down the upload to just lambda bit seed. The client still needs to download the hint. The size of the hint is 1 bit per set, which is lambda times square root of n. Communication in the offline phase. So roughly, right? Yeah, basically O tilde of square root of n, where tilde hides the factors that are polynomial in the security parameter. Then in the online phase, the client just needs to send a single set of size about square root of n, gets back just a single bit. Again, we get communication roughly square root of n. In terms of the time, then in the offline phase, the server needs to process the entire collection of sets, which is is about linear time. And in the online phase, the server only needs to process a single set, which has size square root of n. And as I mentioned before, we can actually use a little bit extra tricks to compress the online communication to be order log n by somehow finding a more compressed representation of these punctuable sets, these sets with I or some index being removed. And yeah, but that kind of, as I said, this comes with a cost at storage. So what I described until now is how to do a single query. And then you can also ask, but okay, how can we do multiple queries? Because we want to amortize the cost of the online phase. So here I'm actually going to skip a little bit over the details. There's a problem that you cannot just repeat the online phase as described more than once, because if you just reuse the same sets in the client hint multiple times, that the server will basically can learn something by seeing that same set over and over again. And so the client needs to kind of resample and resample the sets every time, resample each set every time it uses it, and also needs to make sure that it has the correct parity of the new set, and it can do that by contacting again the left offline server. But it's very similar. It's very similar idea. So yeah, please check out the paper if you're interested, or ask me questions. So this kind of was basically the first part of the talk. We saw how the scheme works in from the more theoretical perspective. Now I want to talk about handling database updates, which again I think people were interested in. But maybe it's a good time to stop for some questions about the first part.
If I may ask a question, this technique seems somewhat similar to parity checks for error correcting codes or error detecting codes. So have you considered some mechanisms from that area in your research? I'm not sure if it's feasible or not, but yeah.
Yeah, I think so. I think there's actually some newer work that actually, I mean, one connection, I think maybe, I mean, first of all, in terms of the technique, there is definitely some connection. There is actually a way that we considered to make the scheme, there's like a different, I mentioned how to avoid failures in the online phase. And one way to do it is actually to use a more complicated error correcting code. So you can imagine that if the servers agree on some error correcting encoding of the database, then the server can basically to read a particular bit from the message, it can actually it needs to read multiple bits from the code word. But even if some of them will fail, then by the properties of the error correcting code, you can still recover the right value. So the parity is like a very simple error correcting code. You need to, in this case, you need the query to succeed to read your bit. But if you encode the database, there is a way to handle failures. We tried this direction, but it turned out not to be very useful in terms of the efficiency of the protocol. But maybe maybe there are some new ideas that potentially can improve the protocol using more ideas from that space.
Thank you.
Okay, let's now see how we move from this very simplistic scheme that allows lookups into arrays of bits into handling dynamic dictionaries and block lists, which we were interested in. So the first part, by moving from arrays to just static dictionaries, as I mentioned, this turns out to be not that difficult. There's you can basically use some data structure and hashing ideas, and for PIR, this was actually there's a technique called PIR by keywords that allow you to do this. The second problem of supporting dynamic, databases is a bit more tricky. And to expand on this a little bit, if in normal PIR, in standard PIR, in which there's no offline phase and there's no hint, then when the database changes, there's actually no problem, because the client can just always run, the client and the server can always just run their queries against the latest version of the database. So if the database changes, just every time you use the latest version. For offline online PIR, database changes are more of a problem, because if the database changes, then we're kind of risking that the hint of the client will now be stale, will not be up to date with the server. So somehow we need to make sure that the state that the client holds is constantly up to date with the database as the database changes. So the naive approach to handle this is to simply rerun, whenever the database changes, throw out the hint that you had and rerun the offline phase with the offline server, generate a new hint. However, this will be very expensive, because remember, the offline phase is the expensive part of the system. And so this would basically require a linear amount of work on each change. We don't want that. Instead, we have a more refined approach that basically does incremental preprocessing. And now the work of the server if each change is only logarithmic in the size of the database instead of linear. And this uses some ideas from the data structures literature for turning static data structures into dynamic data structures. Let's see how this works. So we'll think about our database as being divided into buckets, and we'll have two rules for maintaining those buckets. The first rule is that every new record gets its own new bucket. And second, whenever you have two buckets of equal size, the servers will merge the buckets into a buckets twice their size. So for instance, you have a database, then there's a new update, the update gets its own bucket, then there's a second update, it also gets a second bucket. Now there's two buckets of the same size, then we merge them into a bucket of size 2, and then and a third update comes, it also gets its new bucket, and so on and so forth. Whenever you get two buckets of the same size, you merge them and grow the bucket size. And you can see, using this update rule, basically guarantees the invariant that there is at most logarithmic number of buckets at each point in time, because the sizes are going to be exponentially increasing, and so you have at most logarithmic number of buckets. And now here's how the servers and the client can use those buckets to do more efficient incremental preprocessing. So now the client will basically store a hint for each bucket of the database, and then when a new bucket appears on the server or a new bucket is formed, the client will basically run the offline phase only on that new bucket, and the client will download a hint for that new bucket and store it. And you can see that every record in the database is only going to be preprocessed at most at each bucket. So if every record appears at most logarithmic number of buckets, you run the preprocessing once per bucket, and so you have at most the logarithmic overhead in terms of the amount of preprocessing. And then how do you run the online phase here? When the client wants to read a particular index in the database, first of all it kind of maps it to the correct bucket. So here, if it's just lookup by index, it knows the size of each bucket, so it knows which bucket it needs to query. And then it sends the query of that basically belongs to that bucket. However, to avoid leaking the bucket that the client is now querying, it also sends some dummy queries for the other buckets. The server responds, runs the online phase on each bucket with the query that the client sends it, and the client gets all the responses, but basically the response that belongs to the bucket that the client is interested in, the client uses that hint and that response to output the value of its bit of interest. And here the idea is actually, you can say that the overhead again is at most logarithmic. However, because the sizes of the buckets are exponentially decreasing, that if you do the summation, you actually get only a constant overhead in the online server time. That's the idea of how to handle updates. And now, before I move on to the final part about the implementation and evaluation, are there any questions about the update scheme?
Can the update handle deletion?
Oh, yeah, that's a good question. So yes, the simple scheme I described, not really, but the way we can do it is we basically, we can kind of think about that when you add deletion, you mark the record that you add is basically, you have some special value that says that this is a deleted value, and when you fetch, when the client fetches that value, it knows that it always queries the latest bucket, and we'll see that the value is some special deletion value. It will just know that the record got deleted, and once in a while the server can actually like garbage collect and remove all those deletion marks and just kind of defrag the database and remove those records.
Okay. There is a question in the chat. Does the bucket technique reveal the access pattern of the clients? If not, will it increase the communication costs?
Yeah, that's a very good question. So we do not reveal the access patterns, and the way we do it is that the client always queries all the buckets. So it does increase the communication. I mean, you can say that it increases by at most a logarithmic amount, because multiplicatively, because there is at most a logarithmic number of buckets. So there's like an extra factor of log. But if you're more careful in the accounting, because the sizes of the buckets are smaller, then you can show it's not actually a logarithmic multiplicative factor, but only a constant factor. So it does increase, but not that much. Yeah.
Okay, thank you.
Okay, so this is kind of the schemes, and then we implemented those schemes, and we built our system called Checklist. We built it in Go and some of the more performance critical parts in C. And our target application was the safe browsing application that I mentioned, and so we integrated our PIR client into the safe browsing system. The way we did it, it's just a little bit technical details, is to avoid modifying the browser code and writing the PIR as part of the core browser. What we did is we actually run a local proxy on the client's machine, so on the user's machine, and then in the browser you only do a configuration change that instead of pointing to, where is basically the configuration value that points to the safe browsing server, instead we basically write the URL of the local proxy, and so the browser still thinks it's talking normal safe browsing protocol, but it's only talking to a locally running proxy, and then the proxy translates this request into a private information retrieval request to those two checklist servers that we run in the cloud. That's just kind of a technical detail. And in our PIR client, we implemented both our new offline-online PIR scheme and prior work, so standard PIR using the DPF-based PIR, which is very fast. And then to run our experiments, what we did, we actually ran our proxy on a kind of collection-only mode. So the proxy would actually talk to the real safe browsing servers, but we'll see on our own laptops the pattern of requests and responses. And from this log of requests and responses, we can actually deduce the frequency of lookups, the frequency of updates to the database, how much does the database growth daily, and what's its size roughly. And then when we have this trace of requests, we can actually replay it using our PIR scheme with our PIR servers and measure the different performance metrics. So first of all, we can look at the amount of server work, which is one of the core metrics that we try to optimize. And we can see that our new offline-online PIR is more efficient than traditional PIR. So it uses a roughly 5.5x less computation on the server than prior work, than traditional PIR. So here on the x-axis, you basically see kind of the time horizon. So the user using the system for a few months, and the cumulative server time that the server spends on responding to those queries. So we save on server computation, but we lose elsewhere. So in particular, our new offline-online PIR scheme is less efficient in terms of less efficient in terms of client time. So we use 9x more computation on the client than prior work. And part of it is because it's basically to look through this collection of sets that the client stores locally requires a lot of time for the client. If you're wondering kind of about the trade-off, then you can imagine that in some setting where maybe the user cares about its privacy, and maybe the service provider doesn't have a lot of incentive to deploy a privacy preserving mechanism, then maybe those protocols in which the servers are very efficient could provide an easier path towards service providers deploying privacy preserving protocols, and the users who are interested in the privacy might bear the cost themselves. And if finally, let's look also on communication. Here we can see that our protocol is, again, a little bit less efficient than prior work. It requires 2.7x more communication. And part of it is actually related to the question that someone asked a few minutes ago. The update scheme introduces this constant overhead that results in the protocol being less efficient in terms of communication. So I do want to summarize, kind of finish the talk by kind of summarizing the different approaches using PIR for blocklist lookups, or in this case for private safe browsing. So we know we have the baseline, which is the non-private lookups, the way that safe browsing works today. And we can see how it fares on the different metrics. So server cost, here it's how many servers you need to have to serve roughly 1 billion users, the latency, the client computation, communication, and client storage. And then we have the different privacy preserving approaches. So the first approach is kind of a very simple approach. The client can just download the entire block list and do all the lookups locally. So this would be very efficient in terms of server cost, because it just needs to send the list to the client. However, this will require a lot of resources in terms of communication and in terms of client storage of storing this list. The second approach is to use the classic standard online only PIR, such as the one from distributed point function. Here, it's actually very efficient in terms of communication and in terms of client storage, and not too bad in terms of client computation, but this is very expensive for the server. This goes back to this linear server time that I mentioned that all those classic PIR protocols have. And finally, we have our new approach, the offline online PIR, that balances the server costs and the communication and the client storage. However, we have the higher cost in terms of client computation. So this is for the application for safe browsing, and then you can choose in other applications of block list lookups, maybe with different parameters. You can choose the approach that's right for you. I would say that whatever approach you use, you can see you can get quite a large gain in client privacy, and you can choose from this menu of how you would like to pay for it. Depends on your concerns about the different cost metrics. So again, just to sum up, safe browsing today leaks information about the user's browsing history to the service provider, but with checklist, this is a two-server solution that, as long as the servers don't collude, no additional leakage. There's no additional leakage to either server about the user's browser history. Yeah, and again, just to conclude, I would say that I think PIR is a very cool cryptographic tool. I'm very excited about maybe future work further improving it, and further systems being built for further privacy preserving systems using PIR for other applications. I would say that now the cost of PIR are within the realm of practicality, but still significant in some sense. Privacy doesn't come for free. We have different trade-offs, but I would hope that, again, future works makes it even more practical for other applications, maybe for certificate transparency, DNS, and so on. Yeah, with this, I'll conclude. If you have any questions, please feel free to send me an email or to reach out. And our paper is on ePrint, and our code is open source on GitHub. And thank you so much for attending the talk.
Yeah, thank you. There is a question in the chat from Sasha. The question is, the clients must always first query for updates before querying for data. Is that true?
Yeah, that's a good question. So actually, the short answer is yes, but I would say first the client can do it out of band. It doesn't have to wait for the query. It can, in the background, always make sure it has the latest version. For safe browsing, when I introduced initially safe browsing, remember how I showed that there's basically this compressed list that the browser always stores to make things faster. So we kind of piggyback on this, on the fact that the browser already maintains this list, so it already kind of periodically queries the server to maintain this list, and this is where we actually download our latest hint and make sure that the PIR state on the client is also up to date.
Any other questions? Yeah, see ya.
Okay. With the risk of making a fool of myself, can you please go to the previous slide where you showed the efficiencies?
Mm-hmm.
Yeah, this one. So does this mean that basically, if I'm a client that have a lot of storage, I should go with the full list solution, and if I am a client with a lot of computation available to me, I should go with your solution? Is that?
Yeah, I think that's a pretty good description. I should say for safe browsing, yeah, I think like it's not super clear to me why Google are not considering just having the client download the entire list. Maybe for reference, I should say that the size of the APK on mobile to download. I think we checked Firefox, for instance, is like 60 megabytes. So it would still be kind of significant. You would have to double the size of your application just for this feature. But maybe for desktop browsers, it won't be that bad.
Right. I was sort of, when I read about safe browsing and the hash solution that is currently applied a while ago, I was under the impression that maybe they also have a privacy, I guess privacy concern. They don't want to reveal the sort of all of their set because they consider this as part of the service they provide. Is that also?
I think that's a great point. I think that I agree. I don't know, but I think I agree with your assessment. I think that even if you do like when I mentioned how to add server privacy, you can actually add server privacy to each of these approaches. So even if you download the full list, here's like a strawman of how you would provide server privacy. Basically, the server would encrypt the full list, so the client would download the list encrypted, but the keys to the encryption of record, they can be computed using what's called an oblivious pseudorandom function, or an OPRF. That's and then basically when the client wants to read a particular entry, it just needs to decrypt decrypt a single record, and to decrypt it, it basically evaluates an oblivious PRF with the server, and by evaluating an oblivious PRF, the client can learn the decryption key without the server learning at which point the client is evaluating the oblivious PRF.
I see.
And so basically, what the client would do, the list locally would be a map from partial hash. Yeah, I mean, you could say, yeah, because the list of partial hashes is already leaked to the client. So it will just be a map from partial hashes to an encrypted full hash. And then, yeah, you kind of look up the encrypted full hash, and then you decrypt it with the assistance of the server. So you could do that and gain privacy. You can also use this approach for any of that, like our approach as well. Basically, this is kind of a general transformation from normal private information retrieval to what's called symmetric private information retrieval, where you have privacy also for the server.
I see. Okay, thank you for that. Okay, that's great.
Yeah, thanks so much for the questions.
Thanks.
Okay, there is another question in the chat. The question is, the problem of downloading the full list is how often do you need to update them? So downloading it again.
Yeah, that's true, but I would say that usually you can just download the diffs, so only the recent updates. Of course, it would take some communication, but I think it's more probably of a storage. Yeah, I mean, yeah, I think it would be. I don't know. I would be curious to hear what developers of safe browsing think about that approach.
Okay, right. I have a question. So my understanding is the hints is actually a compression of the database, and it's actually a lossy compression probably, and then it can be recovered with the help of the other server because there is the full database again. So if that is the case, then can we prove that the compression is optimal or not?
Yeah, that's a great question. So actually, in our previous paper, in the Your 20 paper, we actually show a lower bound for this type of offline-online scheme. That's a lower bound on, you can think about it as like the size of the download in the offline phase, or as you say, basically the size of the hint and the online time. In some sense, it's basically a trade-off that if you compress, if you use a very compressed representation, so a very small hint, then you need the online time to be large. And the expression is actually something like the size of the hint times the online time need to be at least n. So this is like you can get square root, or you can get n to the 2/3 and cube root of n, but you can't get like fifth root of n and fifth root of n in both.
Okay. Yeah.
Yeah, that's a great question.